Math 1343, Week 8, Video 11. Test for Association, Critical Value Approach. Well, it's time to put it all together. So far we've talked about what a test for association is, how to state the hypotheses, how to calculate the expected value of each cell in the contingency table based on the totals in the observed values contingency table, and how to calculate the test statistic using the same formula that we used for the test statistic for a goodness of fit test. So now it's time to put it all together. Test for association, critical value approach. From the data in the previous videos, tested a significance level of alpha equals 1% if there is an association between gender and type of degree. By now, you should be fairly familiar with the protocol for performing a hypothesis test using the critical value approach. The first step, as usual, is to state the hypotheses. I'm not going to rewrite them because they are still living right here. The null hypothesis will always be there is not an association between, in this case, gender and degree type, because that's assuming that the proportions are equal and therefore there's no difference whether you're male or female if you receive a certain type of degree. And the alternative would be there is an association because some of the proportions are not equal. Remember, null hypothesis demands equality or allows equality. Alternative does not. Second move in the critical value approach is to calculate the critical value. Well, in our class, we look it up in a table. Calculate the critical value, comma, label the regions. So in other words, we draw a picture. But in order to do this, we need to know a few things. Number one, is it left tail, right tail, or two tail? Well, just like a goodness of fit test, this will always be a right tail test. A test for association is always a right tail test. And the reasoning is the same as before. If what we expected perfectly matched what we observed, in which case the null hypothesis is true, obviously, then each of these subtraction problems would be 0, which means the whole sum would be 0. And since the chi-square distribution starts at 0, it would have to be part of the non-rejection region, and therefore the right tail would be the rejection region. Also, because if our expected values start deviating too much from what we observed, these subtraction problem answers start getting larger, the sum starts getting larger, and if it gets too large, aka too far to the right, we have evidence to reject the null hypothesis. So it will always be a right tail test. Now, being a chi-squared distribution, it requires the degrees of freedom, and I haven't given you that yet. For a test for association, the formula for degrees of freedom is, wait, do you remember what it was for a goodness of fit test? For a goodness of fit test, you had k categories, and the degrees of freedom was k minus 1. It's kind of the same thing here with a little bit of a twist. Recall that we had a 2x3 contingency table, males and females separating the columns, bachelor's, master's, and doctorates separating the rows. If we were doing a goodness of fit test, we would either have one of these classifications or the other. For example, if we were doing a goodness of fit test just for the distribution of degree types, k would be 3 and the degrees of freedom would be k minus 1, which would be 2. But if we were doing a goodness of fit test over just the two genders, k would be 2, k minus 1 would be 1. So how do we go from 2 degrees of freedom to 1 degree of freedom? And the answer is, or 2 types of degrees of freedom, and make it 1 type of degree of freedom? And the answer is we multiply them. The formula for degrees of freedom for a test for association is the product of the number of rows minus 1 times the number of columns minus 1. So for this particular contingency table, we have 3 rows, so 3 minus 1, and we have 2 columns, so 2 minus 1. Now some of you are going to get cute and try to do an algebra move. You're going to try to FOIL this. Stop that. 3 minus 1 is 2. 2 minus 1 is 1. 2 times 1 is 2. So there's a formula for the degrees of freedom. I'm going to move that over here in our list of things. Degrees of freedom equals rows minus 1 times columns minus 1. I can spell. All right, so now we know everything we need to know. We know that it's a chi-squared distribution, so we're going to use the chi-squared curve, which starts at 0. For such a low degree of freedom, this one would actually be the one that looks like a quarter pipe, but I just always by default draw my chi-squareds like that. We know it's a right tail test, so we'll cut off the right tail. And the significance level is still the area of the rejection region, so we have an area of 1%. And part of this move is to label the regions, so our non-rejection region is on the left, and our rejection region is on the right. Now we just have to look up the chi-squared that separates them. And let me go to a table, which I don't have pulled up yet. I can't believe I didn't do that. But if you give me 1 second, I'll just call out the moves that I'm doing for those of you who are happen to be in my class right now. UT website, go into Canvas, going into Canvas, click on this class, and then we will click on modules and go to week 8 and click on chi-squared distribution. And I'm there. So if I go to the second row for this 2 degrees of freedom and go across to the 1% column, which is the second one from the right, I see a chi-squared value of 9.210. 9.210. And now we know the critical value, the CV if you will, that separates the non-rejection region from the rejection region. All right, so step 2 is the same as it's always been. Calculate the critical value or look it up and use it to label the regions in your curve. Step 3 is to calculate the test statistic. And we've already, excuse me, we've already done that. In the previous video, we got a test statistic of chi-squared equals a whopping 565.9662. Yeah, that's just a little bit larger than this critical value. Your fourth move, of course, is to make a decision. And in the critical value approach, the decision is based on whether or not your test statistic lands in the rejection region or non-rejection region. This test statistic, being ridiculously large, lands way to the right. Further than that, lands way to the right of the critical value, so this null hypothesis is very rejected, like Dikembe Mutombo rejected. And if you don't get the illusion, YouTube it. Dikembe Mutombo, M-U-T-U-M-B-O. So you make a decision, and the decision here is going to be to reject the null hypothesis. And as usual, you should answer the question. Well, there was no question stated, but it should be pretty clear where we're being asked, is there an association? So evidence suggests, you should always allude to the evidence. Evidence suggests there is an association. Between gender and type of degree. Now, is that a bad thing? Well, that's kind of subjective. Maybe it is, maybe it's not. Maybe a higher percent of women get doctorates in law studies than men. Maybe it's a higher percent of men. Maybe this or that or that or this. But the fact that this evidence suggests that there is an association might cause somebody to analyze the cause of that association and see if there's a way to rectify it so that there is no longer an association. That's again, that's under the assumption that the existence of association is a negative thing, and it very well could be. But this is very strong evidence because that test statistic was ridiculously large. All right, and that's how you do a test for association using the critical value approach. New information in this video, it's always a right tail test, formula for the degrees of freedom. Other than that, it's just standard protocol for the critical value approach.